same base as the one on the left-hand side. But it needs some algebraic manipulation. I have to do something to it. So the left-hand side is still this, and the right-hand side will be I want to write it with the same base. So how could I do that with this? Excellent. So now here's what I'm saying to you. We are not simplifying E. We're not reducing E. We are not taking it out. We're not erasing it. So here's the concept. Two numbers are equal, and they have the same base. What has to happen to their exponents? One more time. Two numbers are equal, and they have the same base. What has to happen to their exponents? They have to equal each other. So x plus 4 must equal negative 2x. There is no other way because the bases are the same. Okay, I will subtract x from both sides, and I will divide by negative 3. And this is it. Once again, this is a lucky case. The unlucky cases are between 23 and 48. So I'll pick the first one, and then you pick the next one. So for example, 28. 19 raised to the x power equals 143. Why am I saying that this is not a lucky case? It's simply because the left-hand side and the right-hand side will never be presented with the same base. It's not possible. So therefore, I have to apply a mechanism. Do you remember when we had to solve the equation, the square root of x equals 2? What did we do to both sides? Square. Why? We used the inverse operation. We had here the square root, but now we use the inverse operation. What is the inverse operation of an exponential function? Exactly. So I have to apply to both sides a log that I have in the calculator. Well, now I have to stop saying that because Candace showed us that we can, in the new calculators that I don't have one, but in the software, we can plug in any base we want. So I will apply still either natural log to both sides or common log to both sides. It doesn't matter, but it has to be the same on both sides. Now, there is a property of log that says that log applied to a power, what does it do to the power? Exactly. It becomes a factor, goes in front, it becomes a factor, so it's multiplied. If you remember, I said last time, this is a fancy looking number, but it's just a number. Natural log 19 is just a number. There's no variable in there. It just looks like it's different, but it's not. If you plug in the calculator, you're going to get a number. If you plug this in the calculator, you'll get another number. So now, what do I do to get x by itself? By this number, whatever that is. So natural log 143 divided by natural log 19. This is not natural log of 143 over 19, but it's this number divided by this number. So I'll put in the calculator and get the answer. And it's done. So natural log 143, close the parenthesis, divided by natural log 19. And that's the answer. So if you want the exact, this is the exact. If you want to approximate, I will say 1.69.
Is there a reason why you put the 143 in now?
No, because x is multiplied by this number. I cannot divide by this. I divide by the number that multiplies x.
Okay.
Right? I have no choice. I can't play with that. So I have to divide by the number that multiplies. Good. Now, the most difficult exponential equation is this one, 42. The most difficult, why? It has a lot of steps. A lot of steps. Because we are not going to approximate till the very final step. Can I present 7 and 3 with the same base? Absolutely not. So I have to apply a mechanism, like I applied a mechanism here, that canceled this. The same thing, I have to apply a mechanism here that cancels the power, brings the power down. And there is only one function that does that. So what do you want to apply? Let's apply this time common log. It doesn't matter. As long as I apply common log to both sides, it does not matter.
You can switch LN or
One or the other. Yes. But as long as you apply the same to both sides. So now 2x plus 1, if you forget to put it in parentheses, the whole thing collapses. Because now the factor in front is the whole thing, 2x plus 1. And then log 7 equals x plus 2 times log 3. One more time, I know it till we get used to it. It's a little bit hard. This is just a number. I know it looks fancy and so on and so forth. It has a log in front of it, but it's just a number. I'm trying to solve for x. What will be the next step? Because I have x on both sides. So one more time, this is just a number, and this is just a number. What should I do? Say it again. Distribute, exactly. So I'm going to distribute this number to these two terms, and I'm going to distribute this number to these two terms. So 2x log 7 plus log 7 equals x log 3 plus 2 log 3. Again, log 3 is just a poor number. Don't be afraid of it. Remember, we are solving for x, but I still got x in this term and in this term. What do I need to do? I need to bring this term next to the other one that has x, and I have to move this term to the other one next to the other one that does not have x. I have to separate the terms with x from the terms without x. So when I do that, I only change the sign, right? When I move a term from one side to the other. So then I have 2x log 7 minus x log 3 equals 2 log 3 minus log 7. It's a lot of steps. I have to distribute, I have to apply log, I have to distribute after that, then I have to move terms around. And now I cannot combine them because they're not like terms. But there is a way, though. If I can combine them, I have the other way. So what is the other way? I cannot combine these two. But there is a way of getting x out of there. Of course, I have to factor out x. So I have 2 log 7 minus log 3. And I'm done. How do I get x finally from there? Divide, because it's multiplied. So I have this whole thing, 2 log 3 minus log 7 over 2 log 7 minus log 3. Now you have to be very careful if you want to approximate this. Very careful how you put it in the graphing calculator, because it can give you all sorts of answers. Okay, so, don't forget parentheses around the top. So left parenthesis, 2 common log, log, 3, close the parenthesis, minus common log 7, close the parenthesis, and close the parenthesis now for the top. And now you divide. Open a parenthesis for the denominator. 2 log 7, 2 log 7, close the parenthesis, minus log 3. Close the parenthesis for log and close the parenthesis for the denominator. And press enter. And we get approximately 0.09. Okay? Okay?
I'm not sure what happened. You were kind of on the right track here, but I'm not sure. We can talk about it again.
Okay. Now, let's move on to logarithmic equations.
I have a question.
Yes.
So back to the original question, yeah, base 7.
Say it again.
So back to the original question,
This one?
we'll have 7 raised to x.
Oh, nobody can see it. Sorry. Thank you. Sorry about that. Yes,
So is that the only way to solve it or not?
the only way. Is there another?
Because I was thinking if the bases are different, I would try to make them the same. That's what I do. So
You could,
so one
but you
7
can't make 7 and 3 with the same base.
Yeah, then when I have the same base in this solve for x.
So you're going to apply base 7 or base 3 to both sides?
Yeah, so they both have.
Yes, but if you don't have a new calculator, you're going to have to change the base anyway. So if you don't have that calculator that allows you to punch in the base you want, you're not going to be able to get an approximation unless you use the change of base formula, which is fine. But you make it more difficult. But if you have that calculator that allows you to punch in the base you want, that's fine. As you know, I don't ask you to use a particular method. If you have a different one, I'm fine. I really am. I strongly encourage my students to choose the method they like best. Okay? Very good. Now, logarithmic equations have a problem. Because the log function is not a friendly function. So I recommend 2 methods. You choose the one you like. You state domain. I'll show you in a moment. Or check. But you must use one or the other. It's mandatory. If you don't like to state the domain, and I'll show you in a moment how I do that, that's fine. But if you forget to check in the final, your prospect solution in the original problem, then you're not completing the problem. You don't have a complete solution. Okay? So I like this. Why? Because sometimes I forget to go back and check.
Sorry, this is section
4.4.
4.4.
Yes. So I prefer this. You may say, I don't like that, but I promise I will never forget to check. That's fine. Okay? So I'll start with 50. And we have log base 5 of x is 3. I don't know what log base 5 of what number is 3. I have no idea. However, I know the most important concept in this chapter. And I know that any log equation can be changed into
5 to the third power.
not before I state my domain. That's okay. No, you're right. You're right. Not before I state my domain. What is the domain of this log?
0 to
Exactly. X must be greater than 0. If the answer I get is not a number greater than 0, I will disregard it. So now, how do I change the log equation to an exponential one? Always start with the base. Yes. So always start with the base and go counterclockwise. 5 to the third is x. So x equals 125. Is this number greater than 0? So I'll say this is it. I stated my domain. I knew that the answer had to be a number greater than 0. If I had obtained negative 125, I would have said, no, it's not a number greater than 0. Equation has no solutions. So you either state a domain and you check against the domain, or you go back to the original problem to check. Okay, one or the other, you have to write something, then say, I checked. Okay, or something like that. So I know you know what you're doing. Of course, this was just a warm-up type of log equation. So, for example, Problem 68. So log base 6 of x plus 5 plus log base 6 of x equals 2. If you're using the domain, stating the domain method, you must state the domain on the raw equation. In this equation, I have two logs. This quantity has to be greater than 0, as well as this quantity has to be greater than 0. I will write both restrictions, x plus 5 greater than 0 and x greater than 0. I will solve them, and I will intersect the solutions. So greater than negative 5 and greater than 0. We don't have to write this. For the next and the next and the next problem, we will just click in a second. So what is the domain? Where the solution, if the solution is not there, it cannot be the solution.
Greater than 0.
Exactly. So where both exist at the same time. They both exist at the same time between 0 and infinity. So again, like in the previous case, it happened. It's by chance that the domain is greater than 0. Now I have to remember how to condense this. So one more time, the domain is stated on the raw equation. Now I want to condense this. And there is a property that allows me to condense, and only log has that property.
Isn't that just what we went over?
Yes. Log base 6 of...
It would be x plus y times the log of x. The log of x
Exactly.
plus 5.
Yes. Equals 2. So now this is equivalent to an exponential equation. Only now I can change it into an exponential equation. Not with two logs. I have to wait. I have to condense it. And after I condense it into one log, now this can be replaced by an exponential equation. Which exponential equation? Always start with the base. 6 squared equals, yes, 6 squared equals x squared plus 5x, and you can multiply those already. So now this is a new equation. This is no longer logarithmic. What type of equation is this? No, it doesn't have a ratio. It's not an exponential. It doesn't have the... No, it's not a radical. It's quadratic, right? So it's x squared plus 5x minus 36 equals 0. And I'm hoping that I don't have to work too hard, and I'm hoping that this is factorable. And it happens to be. How do I factor it?
X plus y x.
Very good. So then it appears that the equation has two solutions. They are. However, you should say, not so fast. And what will you conclude?
Negative 9 is not a solution.
Very good. I don't have to go back and check because I worked hard to find the domain. You can say no, and I'm fine with that. You can say, I don't want to spend my time on finding the domain. I promise I'll go back and check. But if you don't, I'll have to deduct points. So please remember one or the other. You choose. Okay, now feel free to choose any problem from 49 through 92.
So you got, okay.
And that's any equation you want. If not, I will choose. Let's do 90. Very good. And that is log base 2 of x minus 1 minus log base 2 of x plus 3 equals log base 2 of 1 over x. And after this, we can look at word problems, and then we can come back for more equations. Good. I have 3 logs here. So I know that this x minus 1 must be greater than 0. I know that this x plus 3 must be greater than 0. And I also know that 1 over x must be greater than 0. When I solve this inequality, what do I get? X greater than 1. When I solve this inequality, I get x then negative 3. And when I solve this inequality for 1 over something to be positive, that something must be positive as well. So now, without graphing, can we identify the domain? So from negative 3 to infinity, from 0 to infinity, and from 1 to infinity. Of course, we don't need all that anymore. So the domain is 1 to infinity. If my solution does not fall in that interval, I'll say sorry. No solutions. Good. Now I am ready to condense the left-hand side. Can anyone tell us how to condense the left-hand side?
Y base 2 x minus 1 divided by
X, very good. So like before, I don't know why I wrote it so far, so I'm sorry. Like before with the exponential function, bless you. Let me remind you. When we looked at this equation, what did I say? We're not eliminating e, we're not dividing by e or anything like that. Here's the concept. Two numbers are equal and they have the same base. Therefore, the exponents must be the same. Same idea here. Careful. Two logs in the same base are equal. What has to happen to the numbers I apply the log to? They must equal each other. There is no other way. Same concept, because it's the one-to-one property of this function. Perfect. What type of equation is this? Previously, this collapsed into a quadratic. Now, this collapsed into a rational. Correct. How do I solve this rational equation? Exactly, it's a proportion. We must cross multiply. Excellent. So then x times x minus 1 equals x plus 3.
Is there a different way to do that?
Well, you can multiply by the least common denominator, but I don't recommend it. This is the easiest way. But it's up to you, of course. So x squared minus x minus 3 equals 0. Now the rational equation collapsed into a quadratic equation. I'm hoping that this is factorable so that I don't work too hard.
X plus x minus 3, x minus plus 1.
Good. So it appears that the equation has two solutions. What are they?
3 and negative 1.
And you should say not so fast.
Not so fast. You gotta look up and see the domain. So it's x not minus 1. X is not, that's not the solution.
Yep. I wanted to move on to word problems because all word problems change into exponential and logarithmic equations. There are many applications of exponential and logarithmic functions. Many applications. Bless you. So this is the last section of this chapter. Applications. There are three big groups. Exponential growth, exponential decay, and logistic functions. Three big groups in which we will see exponential functions, logarithmic functions, mainly exponential. I want to show you in your book, which I'm not going to, I don't memorize this, and I'm not going to ask you to memorize it. It will be given to you. This is what it's called the logistic growth model. So it looks like this. It looks like a complicated function. It has a number at the top, and the denominator is 1 plus a number times e, base e, raised to negative a number times t. This function will be given to you. You're not going to have to memorize any of this. Okay? So that's the third one. Now, these two are very similar. And we'll talk about them right now, and then the logistic function, but as I said, the function will be given to us. Okay, the exponential growth. Because I want you to see them side by side. Okay, let me give you a few examples of the exponential growth. Bacteria grow exponentially. Rat population, rabbit population, they grow exponentially. What about the exponential decay? We have several examples, but here's the most important one. Radioactive substances decrease their mass in time using an exponential function. Also, exactly. It's all an exponential function. And also, if you remember, I told you that when somebody dies, they determine the time of the death using exponential and log functions. Earthquakes are modeled with exponential and log functions. The temperature is modeled with exponential functions. So, wide variety. So, here is the model. When we talk about the exponential growth, we normally talk about number. Okay? You don't have to write this, just this line, you don't have to write it because I'm going to stick with the notation in the book. But it shouldn't be like that. Okay, so this is the number of T. Number of bacteria, function of time. Number of rats, function of time. Number of rabbits, a function of time. And this is N0, which is the initial value, the initial number that we start with, times e to kt. This makes more sense. Your book shows this, which is fine, but it should be at least a of t, so we know which one is the variable. K is not the variable. K is the exponential growth rate, the rate of growth in percent, but here it's in decimal. And this is the initial number of bacteria or rats or birds or whatever population, and t is time. This one is identical, but it should deal with mass. So it should be m of t equals m0 e to negative kt because it decreases. Instead, your book shows the same thing, which is a0 e to negative kt, which is fine. I'm going to stick with the notation in the book. But this makes more sense because it's talking about mass, and this makes more sense because it talks about population or number. Okay, so let's see how this works. It's a lot of work. I presented a lot of tons of words, but I should show you. Okay, here it is. I'd like to start with problem 8, and let's read the problem. In 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million, and by 2050, it is projected to grow to 12 million. This is page 504. Use the exponential growth model. It's given to us. You don't have to memorize it. A equals A0 times e to kt. So one more time, let me explain what these letters mean. This,
You said what page was that?
504. This is the number today or in the future. It's like an accumulated value. This is the initial, A0, the initial population. This is today or in the future. K is the growth rate. T, time. So they're telling us that in problem 8 on page 504, they're telling us that in 2000, the population was total 3.2 million. And in 2050, the population is projected to grow to 12 million. Use the exponential growth model, which we have, in which t is the number of years after 2000. So t equals 0 represents the year 2000. Use the exponential model in which, okay, to find the exponential growth function that models the data. So they're really asking us to find this. Let's see what we have and what we don't have. So one more time, I don't agree with the book. This should be a of t, which will tell us that the only variable in this expression is t. If I just say a, you could possibly think that k is the variable. You could possibly think that a0 or a0 is the variable. You don't know, right? So it should be a of t. So I'm going to use a of t. Just going to make a little correction for them. So what do I have? I know that in 2000 the population was this, and in 2050 is projected to be this. So is there any portion of the model that I already have?
T equals 0.
You could say that when t is 0, the population is 3.2. I could say that. So population is 3.2 e to k times 0. So this is a point. That's correct. 0, 3.2. Now, can I determine anything from here? How much is k times 0? How much is e raised to 0? So what have I determined? That the initial population, which we knew, but that's another way of determining it. So, million. So I have already determined this to be 3.2. What else am I missing? E is a number. T is the variable in the problem. I found A0, the initial. So what am I missing? K, the growth rate. But I am given a second point. So for now, the model looks like this. A of t equals 3.2 times e to kt. This is the model right now. But I have not used this point. Can anyone give us the coordinates that are hidden, if you want, in that point?
50 would be time.
Yes, because t equals 0 represents 2000. 2050 represents 50. Good. And then, comma? Very good. I want to put this in the model I have right now. So what is on the left? Very good. Equals 3.2 times e, 50k. Excellent. So this is the equation. It's an exponential equation that I have to solve right now. 12 equals 3.2 times e to 50k. Excellent. What should I do first? Exactly. I have to get rid of this. It's in the way. So 12 divided by 3.2, please do not divide. That's not what we are trying to do. Not yet, anyway. And now, this is an exponential equation. The left-hand side has base e. The right-hand side has whatever base. They cannot be presented with the same base. But somehow I have to apply a mechanism that brings 50k down. And there is only one function that will do that. Natural log, because the base is e. Excellent. So I will apply natural log to both sides. Do not do anything with the left-hand side. There is no need. Not yet. Please tell me what to write on the right-hand side. Very good. 50k times natural log E. Let's discuss natural log E. Let's say it's a number y, and let's change this into an exponential equation. What is the base on ln? E. E raised to which power is E? E raised to y is E. Both numbers are equal and they have the same base. What has to happen to their exponents? Right, so then from now on, I'll never forget that the natural log applied to E is 1. So then the equation becomes natural log 12 over 3.2 equals 50k, and I finally have k. What should I do to both sides to get k? Divide by, yes, this by 50. Careful how we put this in the graphing calculator. So natural log, and I have 12 divided by 3.2. You don't need to do anything to it. And further divide by 50. Are you expecting a positive number or a negative number? Since in 2000, 3.2 million, in 2050, 12 million. Positive. Very good. So let's press enter. So it's 2.6%. But of course, I will need it in decimal. So 0.0264 or 2.64%. Part B. In which year will the Palestinian population be 9 million? So this was part A, and this is part B. Now I do have the entire model. I know everything about it. 3.2 times e to 0.0264 t. I have the function now. Now I'm asked, when will the population be 9 million? What should I do to determine when will the population be 9 million?
Use the button on the calculator, e to the 0.02.
You can, because it's t.
I'm sorry.
Yeah, yeah.
Place a times t with value.
So a of t is 9 million. Very good. It's the same type of equation, the same steps. What should I do then first?
Divided by 3.2.
Exactly. 9 over 3.2 equals e 0.0264 t. I need a mechanism that is applied to both sides that will bring that power in front as a factor. Otherwise, I can't continue. I will have to apply natural log. That's the inverse function of the exponential. It's like squaring the square root. Same process. So the left-hand side is natural log of 9 over 3.2, and the right-hand side now is 0.0264 t times 1, and I will not need to write it again. Good. So now, from here, I need to determine t. Top.
Divided by 0.0264.
So let's determine when. So the top is natural log 9 divided by 3.2, and the denominator is 0.0, and so on and so forth. So natural log 9 divided by 3.2, close. Then I divide by the previous answer, because I'm lazy to put it in. So roughly 39 years. So approximately 39 years. Which year will that be? Does it make sense? If 3.2 million in 2000 and 12 million in 2050, somewhere in between, there must be 2039, right? Somewhere in between, they have to have 9 million. Okay. Good. I would like to look at the logistic growth model now. Let's look at problems 43 through 46.
I might be way off topic, but where you have the natural log of e to the power of 0.06
Yes.
t,
Yes.
that becomes 1, right? So wouldn't it be 1 to the power of?
So this is natural log of e to a power. So you have to bring the power in front. So this becomes this times natural log e, which is 1. So you have to have this. Like before. See, we had 50k. 50k is a factor in front times natural log e, which is 1. The power cannot go anywhere. So this power just goes in front. Is that okay? Is that okay? Okay. So 43 through 46 on page 506. We're given p of x. This is given to us 90 divided by 1 plus 271 times e to negative 0.122x. Mod was the percentage p of x of Americans who are x years old with some coronary heart disease. So x is age, and p of x percent with heart issues, problems. So at any age, it will give us the percent of people who have a problem. Problem 43. What percentage of 20-year-olds have some coronary heart disease? Let's read them all. 44. What percentage of 80-year-olds have some coronary heart disease? And then we have 2 other questions. So here's what I recommend. Go to y equals. Clear if you have anything else. And let's put this function in. Since the numerator is just one number, you don't have to put in parentheses. You already know me. I like parentheses, top and bottom, so I don't forget. So then 1 plus 271 times, careful now, second and e. I always put parentheses. Maybe your sophisticated calculators don't need it, but I will always put it in. Negative 0.122x, close the parenthesis, go down, close the parenthesis again. So I punched in this function. So it's 90 over 1 plus 271 times e to negative 0.122x. Now I go to second and table, and I punch in the 20-year-olds. I punch in the 80-year-olds, and I got my answers. So the first one is 3.7%. So P of 20 is 3.7%. The second one is 88.6. P of 80 is 88.6%. What does this mean? Somehow, as expected, that at the age of 20, not too many people are expected to have heart issues. But at 80, a lot of people are expected to have heart issues, almost 89%. Okay? Part B, not part B, 45 and 46. At what age is the percentage of some coronary heart disease 50%? So this is 45 and then 46, 70%. So 50 and 70. What do I do now?
Same thing, you just plug it in to the table. 15.
Careful. So this is percent. This was age. So how do I determine at what age about 50% of the people in that group? P of x now is 50. So 50 equals 90 divided by 1 plus 271 times e to negative 0.122x. I have to caution you that this is not a trivial problem. So this is still a proportion. I still recommend cross multiply. So careful, let's cross multiply. What I would have liked to do is do this. I'm allowed to do this, to swap. But it doesn't matter. If you think it's better to do this first step and then divide, that's fine too. So 50 in parentheses 1 plus 271 times e to negative 0.122x equals 90. I have to divide by 50. So it's 1 plus 271 times e negative 0.122x equals 9 over 5. Okay, what now? Because the equation is far from being ready for the final step. What do I need to do next? I must get rid of, I'm far away from there yet.
Subtract 1.
I have to get rid of 1. I have to subtract 1 from both sides. So 271 times e to negative 0.122x. 9/5 minus 1 is 4/5. I still have one thing that is in the way.
You divide by 271.
Exactly. I'm going to divide both sides by 271. I'm cleaning it up, getting it ready for applying log. Don't have to worry about this. Just leave it alone. You are multiplying both sides by 1 over 271. Now, yes. Now I'm ready to apply log. And natural log is the best because this is e. If it were 10, I would have applied common log. So natural log, natural log. What do I have on the left? Because I know this is on the right. I have a number. I don't care for.
Negative 0.122.
Very good. Times x. So this goes in front, and this is 1. So this is natural log of 4 over 5 times 271. Final step towards finding x. By this. I will let you do the other one for 70, but let's do this now. So let's determine at what age about 50 of us, 50% I should say of us, may develop heart problems. So second, get out of there, clear. I'm going to have to clear. So I have natural log, and be very careful now, 4 divided by, in parentheses, 5 times 271, because the calculator has to perform the denominator first. So close and close again. And now divide by, in parentheses, careful, negative 0.122 and close. So roughly at what age? About 48. So at about 48 years old. So 48 year olds may develop, according to the model, if the model is correct, about 40. When we get to 48, it's possible that 50% of us may have some heart issues. So let's do 70%. So let's work on 70%. Give me the equation, and let's work on it for a minute. And then I would like to work on one more problem, and then we'll stop. So can you please tell me what to write? Excellent. So please perform the same steps. And this is the logistic growth model, logistic function.
What, I'm sorry, what number is this?
This is problem 46 on page 506. Let me know what we get.
Where are you getting? We're not gonna cross multiply.
I didn't, but I already swapped the two to make it easier. But after you cross multiply, that's what you get. You still have to divide by 70. Right? So if I had swapped these two, I would have gotten 1 plus this equals 9 over 5. And this is what I did here. When you swap these two, you get 90 over 70, which is 9 over 7. And this is up here. What would be the next step? Very good. 9 over 7 minus 1 is minus 7 over 7, which is 2 over 7. And then, what do I need to do next? Yes? And now this is completely cleaned up. For what?
H by ln.
Yes. So I apply natural log to both sides. What is on the left-hand side? And that is a number. I don't need to worry about it right now. But I know that I have to do what to both sides to
Divide.
So what I'm going to do, I'm going to go to the graphing calculator and overwrite. So I go to second and entry. So my 4 is actually a 2 right now. And my 5 is a 7. That's all I need to do. So this is a 2. This is a 7. And I press enter. And I get roughly around the age of 56. Very good. Now I would like to look at a problem concerning the exponential decay. So the formula for the exponential decay is identical. It will be given to you. It's identical with the exponential growth. However, there is a negative in front of the rate because it decreases. So let's look at problem 27. The August 1978 issue of National Geographic described the 1964 find of bones of a newly discovered dinosaur weighing 170 pounds, measuring 9 feet, with a 6-inch claw on one toe of each hind foot. Okay. The age of the dinosaur was estimated using potassium 40, which is a radioactive substance. Dating of rocks surrounding the bones. Okay. Potassium 40 decays exponentially with a half-life of approximately 1.31 billion years. Use the fact that after 1.3 billion years, a given amount of potassium 40 will have decayed to half the original amount to show that the decay model for potassium 40 is given by this. Okay. So we are told that the half-life is approximately 1.31 billion years. Let's discuss the half-life. $1.31 billion years. What does this mean? It means that if we start today with A0, let's say a gram of potassium 40, in this time after t equals 1.31 billion years, the initial value, the initial amount, will become half. So if I start with A0, when time is 1.31, then this number, the amount, is half of it. So A0 divided by 2 will equal A0 times e to negative k times 1.31. They're asking us to find the model. Basically, they're asking us to find k. What should I do to this equation to finally or somehow determine k? What would be the very first step? Okay. So let's multiply both sides by 2. That's good. To negative 1.31 times k. What should I do next? There is something that is in the way and I don't have it. What am I going to do? We always try to simplify equations as much as possible. How will I simplify this equation? A0, exactly. Divide by A0. If I divide A0 by A0, what do I get? 1. If I divide 2A0 by A0, I get 2 here, and e to negative 1.31 times k. In order to get to k, I have one more step that we applied before, a few minutes ago. What should I do? Right, so 1 divided by 2 is 0.5 equals e to negative 1.31 k. Now I'm ready for that mechanism that only natural log has and other logs. So I'm applying natural log to both sides. So natural log 0.5 equals what on the right-hand side?
Negative 1.3.
And finally, k is natural log 0.5 over negative 1.31. We're not going to be able to finish part B, but once we have the model, part B is just... Okay, so natural log, in parentheses, please natural log, wake up, okay? 0.5, in parentheses, divided by, in parentheses again, negative 1.31, and close the parenthesis. And we get that the rate, the radioactive decay rate, is 0.5291. And this is exactly what they wanted us to determine. It says a model, so show that this is indeed true. A of t equals A0 times e to negative 0.52912t, where t is in billions of years. Oh. So right here, negative 0.52912t. So we have to determine part B on Tuesday. So here's the plan. The plan is that on Tuesday we are going to review chapters 3 and 4 review, and test 3 a week from today. Today is the 21st, so the 28th. So test on chapters 3 and 4. I will like to post a homework that I would like to collect it on Tuesday so I can post solutions for you. It's going to be 6 problems from chapter 4. Will that be okay? So homework due on Tuesday, 6 problems. Because I would like to go over them and or at least post solutions for you for the test. Is that okay? Thank you. Don't forget your homework. Yes, thank you. Thank you. Yes.
You can fix the practice test that's online.
Is it in Canvas?
Yeah, but when you click on it, it pulls up the practice test from module 2.
It's so hard.